Good morning, everybody, again, to those of you who are already here. And good morning afresh to those who have just joined. So it's 8:05. We're going to get started. We don't have very much to finish up with Chapter 10. So we'll finish that up. Then we'll do some practice problems. Then we'll do some problems from Chapter 9, the homework, that I saw a lot of people were struggling on. And hopefully that will help you understand Chapter 9 a little bit better and prepare you for the final exam. So if you have any other questions, we can also use some of this time as kind of like office hours. So if you have any specific homework questions or any other questions from chapters 9 or 10, you can throw those in the chat as you see fit. All right, so without further ado, let's get on with chapter 10. Last time we kind of stopped around here, so we're going to go through the kinetic molecular theory of gases again, and then keep pushing forward, just to make sure we're on the same page. So, in terms of exam stuff, what you'll need to do is be able to answer like kind of multiple choice questions about the kinetic molecular theory, just like you would have to do with the properties of gases that we covered last week. So this theory, we're talking about gases. Gases are made up of tiny molecules. We already know that. The way that gas molecules move is they move very, very fast, so rapid motion, and they move in straight lines, and they travel in random directions. The gas molecules in a container have no attraction for one another. That means that they don't repel either, so no repulsion. And when gas molecules collide with one another, they do so without losing energy. So they just bounce off of each other and keep moving. The average kinetic energy of a gas molecule in a container is proportional to the Kelvin temperature. The way that that's written is, so Ke is kinetic energy. And that kind of fish sign is proportional to. And that's why we have to use the Kelvin temperature when we do our calculations, because the relationship between the energy of a gas molecule and its kinetic energy is through Kelvin, not Celsius. So are there any questions about this? You just kind of have to know it and answer some simple multiple choice about it. Let me know if you're ready to move on. So related to that, the concept of absolute zero. So the temperature where the pressure and volume of a gas would theoretically reach zero is called absolute zero. And we can't get there yet. We can get really, really close to absolute zero, but we have not achieved absolute zero. And when you're looking at the temperature and the volume, like on this plot here, if you extrapolate all the way back to 0 Kelvin, it's the same thing as negative 273 degrees Celsius. So that is absolute zero. And the final gas law that we'll introduce, which is pretty much the end of the chapter, is the ideal gas law. So the ideal gas law is used to do calculations for gases. Gases, for the most part, behave in an ideal manner. There are some exceptions and things like that, but the kinetic molecular theory, that's describing an ideal gas. And this law gives you a way to calculate pressure, volume, moles, and temperature. So all of these things are related. This R is a constant. You'll be given what that constant is, and it's 0.0821 liter atmospheres per mole Kelvin. You'll be given that along with the equation on the equation sheet, so you don't have to memorize it. And I'll give you an example of how we use the ideal gas law, just like the other ones, and then if you have questions, you can let me know. So how many moles of neon gas occupy 2.34 liters at STP? Looks like we don't have a lot of information here, but we do. At STP, remember that means standard temperature and pressure. Does anybody remember what the temperature is for STP? This is something you will definitely need to know, so if you don't know it, make sure you take down this note, okay? So for STP, the temperature is 0 degrees Celsius, which is the same thing as 273 Kelvin. The Kelvin answer is what we need for the gas law problems. And the standard pressure is 1 atmosphere. So if you see a problem about STP, we're talking about 273 Kelvin and 1 atmosphere. We're given the volume, 2.34 liters, and the question is asking how many moles. So we've got pressure, temperature, volume, and we're looking for moles. That can only mean one thing: the ideal gas law. The only law that we've gone over that has moles incorporated is the ideal gas law. So if you have a question about how many moles, or if you're given a number of moles or a way to get to moles, that means you have to use the ideal gas law. We good so far? All right. So feel free to work ahead of me. I'll put down the ideal gas law and what R is equal to. So if you feel comfortable working ahead, go for it. Otherwise, stick with me. We'll solve it together. I may ask you some questions along the way. And that's how we'll do the rest of these problems. So we know we have an ideal gas law problem. And we're being asked about how many moles. Remember that moles, we're looking at N. So we've got to rearrange this equation to solve for N. To do that, you're going to divide by RT. From there, you just substitute in the numbers and do the math. Now, if you're using a calculator that's not like a TI-89 or an 83, you may need to use parentheses to make sure that the order of operations is done properly. So when you enter it into your calculator, you may need to do it like I'm doing it here. So when you use the parentheses, it tells the calculator do this first. So it will do 1 times 2.34 first, then it'll divide by whatever this product is, the 0.0821 times 273 Kelvin. So make sure to use parentheses. So you should get 0.104 moles of neon. Does this make sense? This is a very simple application of the ideal gas law. Let me know if you're ready to move on, and I'll do another problem, or if you have questions. Then let's do one that's a bit more complicated. What volume in liters is occupied by 3.38 times 10 to the 22nd nitrogen molecules at 100 degrees Celsius and 255 millimeters of mercury? So, let's identify what we have. We've got number of molecules. We've got a temperature. We've got a pressure. And we're asked about a volume. The number of molecules, we can get to moles. Does anybody remember how we go from molecules to moles? So number of things to moles. And this is from chapter 8. Avogadro's number. Exactly. If we use Avogadro's number in a unit factor, then we can figure out how many moles we have. That's our N. And since we have moles, along with temperature and pressure, again, it's the ideal gas law. Does everybody understand how we got there? You may not be given moles exactly, but you may have information to get there. I could also give you the number of grams of a substance along with pressure and temperature and ask for a volume, and you'd use molar mass to figure out how many moles. So all of those things are fair game. So for the ideal gas law, the constant that you have, the 0.0821, that's in liter atmospheres per mole Kelvin. Our pressure is in millimeters of mercury. So that's not going to work. We've got two options. One, we can use a different constant, which I'm not giving you. Or two, we can convert 255 millimeters of mercury to atmospheres. and that's the one we're going to do. So over here, I'll keep a tally of what we did. The first thing we did was convert molecules to moles. Second thing we're doing is convert the pressure from millimeters of mercury to atmospheres. So take a second and convert 255 millimeters of mercury to atmospheres. And I gave you the unit equation. There's 760 millimeters of mercury in 1 atmosphere. Let me know what you get in the chat. And just to help you out a little bit, I'll fill in this unit factor here. We're trying to get to atmospheres, so that should be on top. Millimeters of mercury at the bottom. Anybody get an answer yet? Yeah, we don't have to round it yet. So we're going to keep an extra digit. So we've got our pressure in atmospheres. We know how many moles we have. Now we've got to figure out what it is we're solving for, and that's the volume. So we need to rearrange the ideal gas law so that we're solving for volume. You just have to divide by pressure. And again, feel free to work ahead of me. And if you want to share your answer, you can. Again, with the parentheses, if you're using an older calculator, oops. So our temperature is 100 degrees Celsius. That's 337 Kelvin. Let me try that number again. 373 Kelvin. It's still early for me too. So when you're putting this into your calculator, you may want to use those parentheses so that you get all of the multiplication at the top, and then divide by the 0.3355 atmospheres. So we're looking for a volume. Volume here is in liters. So you should get 5.12 liters. So does this problem make sense? There are several steps before we could actually use the gas law. So I tried to lay it out for you what we did. Questions? You need me to go through it again? Or are you good? So when it comes to the units, let me write it. I'll write the units out with no numbers in a different color. When you are looking at, it's in a fraction, right? So what it really means is this: moles times liters times atmospheres times Kelvin over atmospheres moles Kelvin. And it cancels out. So these on the bottom here, if you're writing it out, those units, the moles times Kelvin, would actually be in the denominator, so that it cancels out the moles and the Kelvin on the top. Does that help, Camden? You're welcome. Feel better, by the way. I appreciate you. 8 o'clock is strong when you're not feeling well. All right. Other questions, or let me know if you're good, because this had, again, 3 steps. We had to do 2 things before we could even get to using the gas law, and I don't want you guys to get tripped up over it. All right, y'all are quiet. I'm going to take that as y'all are okay, or you don't want to say anything. And we'll just keep moving on. Alrighty, so now we're just going to do some practice. So all of the gas laws that we covered are fair game. So that was Boyle's law, Charles's law, Gay-Lussac's law, combined gas law, and the ideal gas law that we just went over, plus partial pressures. So that's several gas laws, all right? So you'll definitely want to thumb through your notes and make sure that you have those things in there. So like I said, I'm going to kind of go through these and solve them, ask you some questions along the way. If you feel comfortable, go for the gold. Try to solve it yourself, share your answer, or just compare it to mine at the end, whichever you prefer. All right. So we've got a deep sea scuba tank that has oxygen and helium gas. If the partial pressure of the gases are 3,300 millimeters of mercury and 125 atmospheres, what is the total pressure in atmospheres? So we've got 2 partial pressures. One's in millimeters of mercury, one is in atmospheres, and we need to find the total pressure. So this is going to use Dalton's law of partial pressures, where the total pressure is equal to the sum of all the partial pressures. So we've got oxygen and helium. Now we're supposed to give the answer in atmospheres, but one of our pressures is in millimeters of mercury. So the first thing we have to do is convert the millimeters of mercury to atmospheres. So when you do that, you should get, I'm going to give you several decimal places here. We don't want to round yet. So you should get 4.34 something something atmospheres. Now that we've got atmospheres for both partial pressures, we can add them together. So we just did addition, and that means that we need to do our sig figs a little bit differently. So I'll line it up for you so you can see. So your calculator will again tell you this big long number. But with sig figs, we can't keep all those. We can keep everything to the left of this red line, which means that we need to look at the 3 to see if we round up or stay the same. We stay the same because it's a 3. So with sig figs, that's our answer, 129 atmosphere. So how did that problem feel? Any questions? Okay. I really do encourage you to try these problems on your own. I also posted some Chapter 10 practice problems and an answer key. So try those as well. Make sure that you really get it. And here's a long problem. The decomposition of baking soda produces carbon dioxide gas. If 42.5 milliliters of wet gas is collected over water at 25 degrees Celsius, 764 millimeters of mercury, what is the volume of dry gas at STP conditions? And then we have the vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury. There's going to be a couple of steps here. We talked about collecting gas over water, how that's called wet gas. Wet gas means that you've got water vapor plus whatever gas it is you're trying to collect. To figure out how much of your gas you have, you need to use Dalton's law of partial pressures. So that's going to be the first step in our plan. Once we have that pressure, we have to answer a question about volume. And it looks like what we have in the problem is a volume, a temperature, and a pressure. When we have all three of those things, that means the combined gas law. So I highly recommend that you put together a plan of how you're going to get from point A to B before you start writing out numbers and doing math on your calculator, because it's very easy to get lost. So does everybody see how we're going to get from this problem to the actual answer? We got to use the partial pressures and then the combined gas law. Let me know if that makes sense. So the first part is easy. We know our total pressure is equal to 764 millimeters of mercury. We subtract the pressure from the water vapor, which is 23.8 millimeters of mercury. We're not going to round here yet. So this is the pressure. Oh, whoops, I wrote atmospheres. It should be millimeters of mercury. We're not rounding yet because that's not our final answer. We're just trying to figure out what is the pressure of our gas. Now that we've got it, we can use the combined gas law. So let's see what variables we actually have and what we're solving for. So the question is asking about the volume. That means we're going to be solving for V2. The things that we can fill in already, our initial pressure, that's what we solved for initially. That's the 740.2 millimeters of mercury. The initial volume is 42.5 milliliters. We were already told that in the problem. And the initial temperature is 25 degrees Celsius, which is the same as 298 Kelvin. And remember, for the Kelvin, you're taking the degrees Celsius and adding 273. So just in case that jump seemed a little weird to you, that's what we're doing. I'm just not writing it out every time. Our second set of conditions says what is the volume of dry gas at STP conditions. So what is our pressure if it's standard temperature and pressure? We just talked about this a couple of questions ago. It's 1 atmosphere. 1 atmosphere is the same thing as 760 millimeters of mercury. So make sure that your pressures are in the same units. The volume, we don't know. That's what we're asked for. But whatever number we get, it's going to be in milliliters, because that's what our initial volume is in. And then our temperature, what's the temperature for standard temperature and pressure? Right. It's 273 Kelvin. Now we've got to rearrange and solve for V2, which first what you need to do is cross multiply. Then we solve for V2 by dividing by P2 times T1. Then you add in the values that we actually have. Try that in your calculator and let me know what you get. And don't forget your units. Yep, 37.9 milliliters. That's our final answer. So to recap, the first thing we had to do was use the law of partial pressures to figure out what the pressure of our gas is. We used that pressure in the combined gas law along with all the other variables to solve for the volume of dry gas at STP conditions. Questions here? Or let me know if you're good. Alrighty. We've got a couple more gas law problems, and then we're going to do a couple of Chapter 9 problems from the homework. So once we're finished that's it. We don't have any more class. We just have office hours. So I hope you're enjoying yourself as much as you can at 8 a.m. with chemistry. So here we go. We've got a sample of fluorine gas, and it occupies 855 milliliters at 710 millimeters of mercury, 255 degrees Celsius. What is the mass of the sample? What gas law do you think we can use here, since we have to end up talking about a mass of a sample, which is in grams? Just take a guess. What ideal gas law? I just gave it. But what gas law do you think we should be using here? Yeah, gave it away. But here's the reason why. We're given a volume, a pressure, and a temperature. What we're trying to figure out is the mass. And the only way to get to mass is through moles. So that's the plan. We'll use the ideal gas law to calculate the number of moles. And then we'll use the molar mass of fluorine gas to calculate the grams. So a few things. Remember that R value our pressure has to be in atmosphere, and our volume has to be in liters. So we've got a couple of conversions to do. We'll start with the pressure. And again, 1 atmosphere is the same as 760 millimeters of mercury. So we need to convert pressure to atmosphere and volume to liters. So when you do that out, you should get almost 1 atmosphere. We're not rounding here yet. We're not at our final answer. For our volume, we've got 855 milliliters. That conversion should look a little bit familiar because we were doing those in chapter 2. And then I'll write out the temperature as well, just because I haven't been doing that. So we've got 255 degrees Celsius. You have to add 273 to get Kelvin. So these are the numbers we're going to use in the ideal gas law. We need N, so we're going to divide both sides by RT. So we just did several things here. I want to make sure we're good with this. We said we've got to use the ideal gas law first. Given that our constant, the R, is in liter atmosphere per mole Kelvin, we need to make sure that that's what all of our units are for the volume and the pressure and the temperature. So we converted the pressure from millimeters of mercury to atmospheres, the volume from milliliters to liters, and the temperature from degrees Celsius to Kelvin. Then we rearranged the ideal gas law to solve for N, which is the number of moles. Now we substitute in all of our numbers. And what you should get for N, there's quite a few numbers there, but we'll only take that many. So that's the number of moles of fluorine gas. Remember, fluorine gas is one of those diatomic molecules. So it is F2. That's important for calculating the molar mass. The molar mass of fluorine gas is about 38 grams per mole. I think on the periodic table you have it might be like 18.999 or something like that. But if you use 19, it'll be fine. So we take the number of moles use our molar mass. Your calculator will tell you something like 0.6999 something or other. But we can only have 3 significant figures. So that means that our final answer is 0.700 grams. So there were definitely a few steps before we could get to the final answer. First, we had to make sure everything had the proper units to go into the ideal gas law. Then we used the ideal gas law to find the number of moles of fluorine gas. Using the moles and the molar mass of fluorine gas, we were able to calculate the grams of sample. You'll definitely see a problem like this on your exam. So just to give you the heads up, definitely know how to do this one. All the others are fair game too, but you'll absolutely see one like this. So the 0.0821, that's the gas constant R. So it will always be in there somewhere whenever you're using the ideal gas law. And we rearranged the ideal gas law here. Let me use a different color. We divided both sides by RT so that we can solve for N. Does that help? Okay, yeah. So whenever you're doing the ideal gas law, don't forget about R. Okay. So that's the last gas law. Oh no, I lied. I have one more gas law problem. We'll end with a simpler one. So you have a 125 milliliter sample of argon gas. The pressure changes from 705. Oh yeah, I can go back. My bad. And I'll post this too. The PDF of the notes. You're very welcome. So last gas law problem. 125 milliliter sample. Changes in pressure from 705 torr to 385 torr. Temperature remains constant. What's the final volume in liters? So we have a volume and pressure. We have another pressure, which is our final pressure. And we're asked for the final volume in liters. Our initial volume is not in liters, it's in milliliters. So you have to convert. Now that we've got all our variables, we did that quick conversion. What gas law do we have to use? We've got pressures and volumes. So that has to mean Boyle's law. Boyle's law says that the pressure and the volume are inversely proportional. So if one goes up, the other goes down, and vice versa. Here we've got a pressure starting at 705 torr, and it goes to 385 torr. For our pressure change, did we increase the pressure or decrease the pressure? We decrease the pressure. And if the opposite has to happen to the volume, then what do we expect for our volume? Increase or decrease? It should increase. So when we're going through and we do our math, let's make sure to check with our logic and see if they agree. We're solving for V2. So that means we're dividing by P2 on both sides. Then we put in our numbers. You should get 0.229 liters. And that makes sense. We said the volume would increase, and that's what we got. questions here, or are we good to move on? Okay. Now we are going to shift gears a little bit. We're going to go backwards to chapter 9. I know some folks are having some issues with some of the questions on Mastering Chemistry. So I went and pulled a couple of problems that I saw people were struggling with. So we're going to do a couple of those just so that you understand how they're supposed to be done. So we'll call this a little bit of a chapter 9 review. So we've got an electric current that's passed through water, and you liberate hydrogen and oxygen gases. What STP volume of oxygen gas is obtained from the electrolysis of 90 milliliters of water? The first thing you have to do here is write a chemical equation. You don't have one, and chapter 9 is all about stoichiometry. If you're doing a stoichiometry problem, you have to have an equation. We're told what the equation is. We've got current going through water, and we make hydrogen and oxygen gases. But this is not balanced, so we have to do that next. On the reactant side, there's 2 hydrogens and 1 oxygen. On the product side, we've got 2 hydrogens and 2 oxygens. We are going to multiply by 2 on the reactant side and see where that leads us. Now we've got 4 hydrogens and 2 oxygens on the reactant side, and still the same 2 and 2 on the product side. Multiply by 2 in front of the hydrogen gas, and we should be all balanced. But always double check. So we've got 4 and 2. And 4 and 2. All right, now we've got a balanced equation. The second key, so I'll kind of try to keep track here. 1, we had to write a balanced equation. Second thing that we have to do, we have milliliters of water. We need to know what that is in terms of a mass. The density of water is 1 gram per milliliter. So for every 1 milliliter of water, you have 1 gram of water. So those are the 2 key things that you needed before you could solve this problem. Does this make sense? I don't know if everybody got to this problem, or if you got to this one you were just so frustrated that said, give me the answer. But does that make sense so far? No. Okay. So, first step, we had to write an equation. And we were told what the equation is. Okay, the density. So let's see. So the density you need because you're told the volume of water. But the volume of water doesn't help you. Water's a liquid. So in order to get that to something more useful, we have to convert it to mass. If water were, a gas, then we could use a volume. But it's not. We're talking about liquid water. So we need a mass of water so we can convert that to moles of water and use a mole-mole ratio to figure out how much oxygen we make. Does that make more sense? And yes, you have to balance the equation before you can do anything, because your balanced equation gives you the mole-to-mole ratio. Cameron, did you have any specific questions, or are you okay now? Okay. Good. Alrighty, now we're all on the same page, I hope. And if you're just kind of chilling, observing, that's fine too. I like to know that you're still there, that you're still with me. But the last part of this is figuring out what kind of stoichiometry problem you have. We have a mass of water, and we're trying to get to the volume of oxygen gas at STP. So this is a mass to volume question. Let's write out our plan. We're going to take our grams of water, and we're going to convert that to moles. Oops. Instead of writing that, and that's using the molar mass. Then we go from the moles of water to moles of oxygen gas using the mole-mole ratio. Then we take those moles and convert to a volume using molar volume. The molar mass of water, it's about 18. It's like 18.02. Something in that ballpark. We're starting with 90 grams of water. That will get us to moles. Then we have to write the mole-mole ratio. This is why you have to have that balanced equation. So it's always the B over A. So our B is the oxygen and the A is the water. So you look at the equation, you see what's in front of oxygen. There's nothing in front of oxygen, so we'll say it's 1 mole. In front of the water, we see a 2. That's our mole-mole ratio. The last part is to use molar volume. 1 mole of gas at STP has a volume of 22.4 liters. And that's from chapter 8. So we're going to use this unit equation to write a unit factor because we need to get the number of liters. We need a volume. So when you put all that together, you should get 55.9 liters. Now, I just chose 90 milliliters, just kind of out of a hat. So that may not have been the variable that you got. But the process is the same. So hopefully that makes it make a little bit more sense to you. Again, the key things were writing a balanced equation, because you have to have that for stoichiometry problems. And 2, remembering that the density of water is 1 gram per milliliter. So if you have 90 milliliters or however many milliliters of water, then you have that many grams of water. And you can convert that mass to the volume of oxygen doing a mass to volume problem. So let me know if that makes sense or if you need me to run through it again. And for the record, you can always let me know. You can always let me know when you have a problem with the homework. Take a screenshot and send it to me, and I may be able to help you out. So, we have a question. Why do you need to do moles of water and moles of oxygen? So, the mole-mole ratio, which is what this is, that helps us to convert from one substance to another in a chemical equation. So it just tells us if we have 2 moles of water, we're going to make 1 mole of oxygen. That's the relationship between the two. Without that relationship, I can't tell you how much oxygen we'll make given the amount of water we're starting with. Does that make sense? You're welcome. Okay. So there were other problems kind of like this where you had to write a chemical equation out first. So I didn't pull one of those. The next one that I pulled was this one here, where you were given a chemical equation, but it was not balanced. So if you're trying to do something with this, you're not going to get the right answer. So how many grams of calcium hydroxide must react to give 1.59 grams of calcium phosphate? So again, this is unbalanced. You have to balance it first. So I'll show you how I do this on this slide. And then on the next slide, I'll solve the problem because I will not have enough room to do both. And if you struggled with writing chemical equations, balancing chemical equations, this is some good review for you as well. So I'm keeping together the phosphate ion as well as the hydroxide ion because they appear on both sides. You see PO4 here, PO4 here, hydroxide, hydroxide. We don't see any oxygens or phosphorus or anything outside of these ions. So we can keep them together and make our lives much simpler. We take a tally of how many of each ion or element we see. And it becomes very clear this ain't even close to balanced. Let's start with balancing the calcium. Our lowest common denominator is 3. So we're going to multiply by 3 on the reactant side. And we'll see where that takes us. Again, you're more than welcome to do this alongside. You don't have to just watch me. If you learn by trying, go for it. So we didn't change the sodium or the phosphate, but we did change the calcium and the hydroxide. We've now got 3 calciums and we've got 6 hydroxides because we've got that subscript 2 there outside of the parentheses. So that means there's 2 hydroxides in that compound, and 2 times 3 is 6. We haven't changed anything on the product side. Now let's go and try to figure out the hydroxides. Lowest common denominator is 6. So we're going to multiply by 6 on the product side where we see the hydroxide. That means putting a 6 in front. That's going to change our sodium. So let's see what we've got. If you feel comfortable to do this without making a table every time, go for it. But when I demonstrate it, I like to make the table just so you can see what changes are happening and keep track of what we're doing and what we're changing. So after this time, we haven't changed anything on the reactant side, but we did change the product side. We've got 6 sodiums now, along with 6 hydroxides. We've got 3 calciums and 2 phosphates. So the sodium and the phosphate are the 2 things that are still unbalanced, and they're in the same compound on the reactant side. So whether you multiply the phosphate by 2 or the sodium by 2, you'll get the same answer. And we do our final check. All right, so we've got 2 times 3 equals 6 sodiums. We've got 2 phosphates, 3 calciums, 6 hydroxides. On the product side, we've got 3 calciums, 2 phosphates, 6 sodiums, 6 hydroxides. So that checks out. We've got a balanced equation. Only took a whole slide to do it. Okay, so that's part 1, balance the equation. I'm going to go on to the next, I'm not going to go on to the next slide because I don't have enough space. So we balance the equation. Now we have to do a mass to mass problem. And I'll write it out, I guess, right here. So we've got the molar mass of the calcium hydroxide, which I calculated these already, and the molar mass of the calcium phosphate. We'll start with the number of grams of the calcium phosphate and use the molar mass to get to moles. Then we have to use a mole-mole ratio, which we get from our balanced equation. We're trying to figure out how much calcium hydroxide, so calcium hydroxide goes on top. And the moles of calcium phosphate go on the bottom. Then we use the molar mass of calcium hydroxide to figure out the number of grams. So there's your final answer. Again, I just made up the 1.59 grams, but it's the same process no matter what number of grams you started with. Balance the equation and then do a mass to mass problem. Let me know if that's good for you or if you have some questions. Okay. Yeah, I can go through the mole ratio again. So for the mole ratio, I'll write that stuff in green. What we're looking for is what we want over what we have from the balanced chemical equation. What we want in this case is the grams of calcium hydroxide. So that means the moles of calcium hydroxide have to go on top from the equation. So that's 3 moles. What we already have information about is the calcium phosphate. We look at the equation there, there's no coefficient, so it's a 1. And that's the mole-mole ratio. Is that good? Good. All right. We've got one more problem, and that's it. So we're absolutely going to be done early with this class. This is another one of the ones where you have to balance the equation first, and then you can figure out the problem. This is a combustion reaction, which we didn't talk about combustion reactions specifically, but anytime you're taking a hydrocarbon, something that's got just carbons and hydrogens, and you're burning it in the presence of oxygen, you make carbon dioxide and water. So that's a combustion reaction. We've got to balance it before we can figure out how many moles of butane gas react with 2 moles of water. So if you want to, go ahead and balance it with me, or just watch. Go ahead. Your choice. Oops. Don't want to do it in green. So we've got carbon, hydrogen, and oxygen. On the reactant side, I see 4 carbons, 10 hydrogens, 2 oxygens. Product side, we've got 1 carbon, we've got 2 oxygens, and 2 hydrogens, and we've got 3 oxygens. And oxygen is in 2 places, in the carbon dioxide and the water. So balancing this is going to be a little bit more tricky. Let's start with the hydrogens. See where that gets us. Seven oxygens. Okay. So we're going to have to do something with fractions here soon. And I wrote the wrong number here. This should still be a 1. So now we're going to balance the carbons. And now we've got 8 plus 5 gives us 13 oxygens. That's an odd number. We have O2. The way that you get rid of The way that you do this is you use a fraction, and then you have to multiply. We did a little bit of that, but this is definitely kind of a challenge problem. So if we've got 2 oxygens, we need to get 13. Well, 6 O2s would give us 12 oxygens. Where did the 5? Okay, so remember, we've got oxygen in 2 places, here and here. So 4 times 2 gives us 8. And then that's 8 oxygens. Plus we've got another 5 oxygens from the water. So we add those 2 together to get the total number of oxygen atoms, and that's 13. The 5 is from when we balanced out the hydrogen. Okay. So if we had 6 oxygen molecules, so add it. No. So I added it all along. Unfortunately. So here, where you see the 7, it's 2 plus 5. Yeah. Not a problem. So now we got to deal with the oxygens. We're going to have to use a fraction here. If I wanted to have 12 oxygen atoms, then I would say 6, right? And that would be 12 oxygen atoms. The other way that I can write 6 as a fraction of something over 2 would be 12 over 2. They're the same thing. 12 divided by 2 is 6. 6 is 6, right? If I wanted to have 13 oxygens, I can write 13 over 2. And that way, I would end up with the right number of oxygen atoms. But I can't leave a fraction there. You have to multiply everything by 2. And again, this is definitely more of a challenge problem. So if you were like, struggle bus, that's okay. I won't purposefully be evil on your final exam. So you multiply it out. And that way, you have a balanced equation. And I'll show you that it's balanced. We've got 8 carbons. 20 hydrogens, and 26 oxygen atoms. That's 13 times 2. For the carbons, we've got 8 hydrogens. 10 times 2 is 20. For the oxygens, we've got 8 times 2, which is 16. And 10 times 1, which is 10. And that gives us 26. So combustion reactions, you usually do have to use a fraction and then multiply it out. You balance everything, the carbons and the hydrogens first, then you balance the oxygen with the fraction. Then you multiply by the denominator of that fraction to get whole numbers for the entire thing. So if you're like, still don't get it, that's okay. This, again, is a challenge problem. So the next slide has the same thing on it. I'm just going to write in the coefficients so we can answer the actual problem. So how many moles of butane gas react to produce 2 moles of water? Now that we have a balanced equation, we can just look and write a mole-mole ratio. So we need to put butane in the top. And we need to put the waters in the bottom. I just did that mental math style. I want to make sure that's right. Okay. So that's how you do that one. The biggest issue was very likely balancing the equation. So when you're doing these, so remember there's the extra credit, the chemistry primer. If you're doing a stoichiometry problem, the first thing you should check is make sure that you have an equation and that it's balanced. Then you can actually do the math. So I hope that helps. Are there any other questions about Chapter 9 stuff or anything like that? I'm going to take that as a no. I'm going to give you your reminders because that's it. You have Mastering Chemistry. The Chapter 10 assignments are due on Sunday because we just finished up Chapter 10. Okay, I'm glad it makes more sense. There's no chapter check-in. I'm not trying to have y'all do extra work. It's the end of the semester. And let's just be real. It's been stressful, okay? Especially those of you who are on campus. You're just trying to live and not get infected, and there's just a lot going on. So I'm not trying to add to your burden. We got to do some work, but I'm not going to add extra on top of extra. Don't forget that I still have office hours this week from 2 to 4 p.m. on Wednesday. If you need time before that in that 10 to 2 time slot, shoot me a message on course messages, and we can set up a one-on-one meeting. There's no class next week. Gobble gobble. Happy Thanksgiving. Get home safe. Be safe. Wear your mask. Wash your hands. When you travel, when you don't travel, all the things. Please be safe. We do have a final exam in December, so make sure that you check your email and check your Blackboard, because I'll have one day of office hours that you can kind of check in, and I'll post a final exam review. So if you have questions on that, then you can just pop in and ask. Other than that, we're done. So I'll be honest, I haven't decided if I want you to do it like exam 4 or if I want you to do multiple choice. Multiple choice is easier for me to grade, but it doesn't allow you to get partial credit. So if you have an opinion, you can let me know. Doesn't mean I'm going to honor it, but at least I'll know. I'm wading through the exam 4s now, and like I said, you get partial credit, which is really helpful, especially for chapters 9 and 10. So let me know if you have an opinion, if you want it to be, kind of that sort of take-home style, where it might be a little bit more challenging, but you can use your notes. Or if you just want a regular old multiple choice or fill in the blank, it is what it is, no partial credit. If you feel comfortable putting your preference, you can. Otherwise, you can send me a course message or say nothing at all. Yeah, I had a feeling people would prefer the take home because it's a little bit more relaxed. You will still have a 2-hour time limit, kinda. So you'll have to upload it, by a certain time on the day that we have the final. So I won't make it too long. Yeah. I hear you. So it will likely be a take-home exam, which is where I was leaning, just because it will be easier for you guys. So I will have it posted much sooner than the day of the exam. And I just want you to post your answers by the end of that day. So your exam is Monday, December 7th at 8 a.m. So it's 8 to 10 a.m. You'll need to have your answers posted by 10 a.m. on December 7th. So you'll have time to work on it. I'll probably give you about a week to work on it and make sure your answers are posted. But again, I'll post all of this on Blackboard. It'll be sent as an email. So you're, 100% up to date on times and all that stuff. I'll also, like I said, post a final exam review. And you can ask questions about that during office hours. I'll probably just do a Wednesday, like I've been doing the week before the finals are due. And then you can pop in and ask your questions. If you have any other questions, let me know. Otherwise, you get 45 minutes of your life back on Monday morning. So you're free to go. You can get back into bed or pull your covers up. It's been a pleasure. Please stay safe, you guys. I'm still here for you, even though it's gobble gobble time. All right?